Welcome everyone to today's Tuesday ARIVE lecture, XR lecture. I'm presenting today. I decided to talk about volumetric pixels, also known as voxels. And our students here know that I'm a little bit of an evangelist for voxels. And I hope I can convince you with that kind of lecture that voxels are a thing which you might want to use in the future. And I will give you a little bit of an intro and what they can be used for, and so on and so forth. Okay, so if you have any questions, then please try. You can ask during the lecture, or you just save it to the end. Doesn't matter. So, okay, let's start with I have to click in here. Probably the. Yes. Okay. It has actually three parts. Three parts I'm talking about. First, I call immersive mixed reality. So we will see what that means. And then I will talk about two things. So one is volumetric video, mainly then later voxel videos and volumetric telecopresence. It means how do we share worlds with by the means of voxels. So let's start with immersive mixed reality. So we came actually up with that kind of term to distinguish it or to set it apart from the normal modes of augmented reality we are aware of. So optical see-through AR, this is what Tobias presented earlier, is you've got some view into the real world, and that is mediated by some sort of virtual content which is brought into your line of sight, normally by way of beam splitters with an optical see-through head-mounted display. The other form of augmented reality is spatial augmented reality. So we use the environment and project into the environment, and that gives us, that mixed reality experience. Then also, as Rob pointed out in his last lecture, video see-through AR. So this is where we bring sensors and normally cameras near to the eyes, to the head-mounted display. So we get a video-mediated experience of the virtual environment, and we mix within the computer the real and the virtual. And then the fourth, immersive mixed reality, also known as remixed reality, where we have sensors, normally cameras or depth sensing cameras in the environment, and we are having an immersive experience of that recreated space around us, normally also including ourselves. So we call that immersive mixed reality. So one quite a well-known paper about that is the remixed reality paper by David Lindelbauer and Andy Wilson. So what they did, they positioned Kinect cameras in a real environment, and then they capture certain elements of that real environment, and then they mix that together with CAD models or 3D models, and then they play through all those different versions of what can be mixed in such an environment, so that it can be experienced as a remixed reality. Actually, my motivation came more from a demo I saw by Dassault. Dassault is a computer-aided design software manufacturer, and they had a demo at IEEE VR 2015. And so what they showed was they had one Kinect sensor, and the user was wearing a head-mounted display, and all they did is they showed the point cloud from the Kinect sensor to the user in the space, and then they mixed that with some computer-aided design model. So, and I got that short video clip here, and I hope it'll work for you guys. So where it is actually filmed through the head-mounted display, and what you see here is that the real environment, and as I said, the point cloud visualized just aligned to the real space in the right way. And in addition to that, they introduce a computer-aided design model, in that case a bicycle, inside of that space. So they mix the CAD model with the real world in an immersive mixed reality mode, because the head-mount display is actually an immersive HMD, right? So the one problem with that approach is actually that it is lacking coherence. So what we saw there were actually two different things. So one was a point cloud, and the other one was a meshed model, and they were brought into the same environment, and they do not really seem to belong to each other in the same place, even if they have been from their location positioned correctly. The bicycle didn't really belong to the real world, because they have been rendered in different ways. So the question would be, if we would both render those domains in the same way, wouldn't we get a better coherence experience out of that. So I'm just pointing to Tobias whether there are any questions in between. I can't see it on my display actually. Okay, so which brings us to voxels, and voxels, just a super brief intro, right? Voxels, from pixels to voxels. So if we consider pixels as perceived gapless colored points in the regular grid in 2D on screens, or any kind of screens, and I have to stress out that it's perceived gapless because normally the emitting elements are more than one, or they're spaced and there are gaps in between those. But when we look at the computer screen, for instance, it appears as a gapless display of colored points in 2D. So the same applies to voxels. So voxels are actually, it's a discrete regular grid in space, and we have pixels, volumetric pixels in that regular space, and they appear as gapless. For instance, not as airy, but they're positioning themselves as a solid experience. So gapless volumetric pixels in a regular grid in space. This is what voxels are, or volumetric pixels. Okay, so our implementation featuring Noel here, hi Noel, is just a replication more or less what the Dassault guys did. So we have a Kinect sensor, which is an RGBD sensor positioned in space, and we just observe the scene with the user in it, and the user is wearing a head-mounted display, and then we bring that kind of these two systems together so that the user get that immersive mixed reality experience. And this is our voxel space. Our space is 2.56 meters in each dimension in the cube, and the 2.56 is because it's so easy then to map that to our voxel space. And then we have a head-mounted display, and we have certain coordinate systems for the tracking camera of the head-mounted display and for the voxel space, and so on and so forth. Okay, so what we then do is we, with the RGBD sensor, in our case with the Kinect, we turn reality into voxel space somehow, and then we can see that here on that photo. So there's a real chair in the environment, and seen from the Kinect perspective, and then translated into the voxel grid, we see that kind of chair in it, which has a certain spatial and temporal noise to it coming from the Kinect sensor, plus some other factors. So, but the same we can do, and we did, and we do, is we turn computer-aided design models, 3D objects, into that kind of same appearance. So we add additional temporal and spatial noise to it, and it looks more or less like if it was captured by an RGBD sensor with some shortcomings, right? And then we combine the two into one world to more coherence. In that case, you can see here Katrin with one real chair and one computer-aided design chair, both rendered into the same space. So to give you an idea how that looks like, I show you a short video clip which I just screen captured at our partners at the University of Oslo in Norway. So this is a first-time user of that first voxel system. So he first, is investigating what is real and what is virtual in that environment. And here Katrin comes in from the side, and but of course she is not really there. So so for the user, it's quite an interesting experience that you see on the table the same, right? There's one real object and there are virtual objects, and they're all mixed and mingled together. So they give a coherent experience for that kind of space, right? So then we actually extended that kind of concept, not only using like the Dassault demo with one Kinect camera, but of course we want to have want to fill that voxel space as a three-dimensional space. So again, Noel featured here with our second version of the system, where we have not only one Kinect camera, but two more Kinect cameras surrounding the user and the whole capture space. And so we did some studies on it in the same way as we did with the first system. So can people actually distinguish between reality and virtual content, and under what circumstances? And so we used, we voxelized the environment, we voxelized different objects in the environment, like the table, or here we see that little green mouse. But we also do that CAD modeling and voxelization as well. And in addition, we also capture different people and put them into the environment and probe whether people can distinguish between real and virtual. And in most cases, in almost most cases, they can't, right? So that's this coherence trick. We degenerate the fidelity of some objects to a degree that it matches the fidelity of the sensors we have in the environment, and put that all into the same gridded voxel space, which gives us that coherent experience. Okay. So when you think of that kind of concept, and you think of, let's say we come from pixels to voxels, we want to think about what would the volumetric video actually look like. Not a video which you just watch on the 2D screen, a video which you can walk in and can walk around the characters and so on and so forth. And of course, we are not the only ones who think about that, and there are a number of systems out there which do volumetric video recording and playback in different versions. So probably the most high-end and high-fidelity systems of them all, in my opinion, is probably the system which is at the Heinrich Hertz Institute in Berlin, which is a Fraunhofer Institute, which is called VoluCap. And you see here Oliver Schreer, who is one of the inventors of that system. So it's a purpose-built space to record volumetric videos and then to be played back on different devices. And so I show a short, marketing video clip of theirs. So they installed one version in a cinematic studio. You see here, this is the system as they build it up. So it's quite a complex system, as you can see, but they can also control the lighting very nicely. And then they record, for instance, real actors in the space to introduce them later into virtual scenes. And as you can see from the quality in a sec, this is a recording phase with the cameras around them, and then they put them into some virtual scenes. So it's actually quite a very convincing experience, I have to say. And their system, is targeting mainly film production, but they also have some versions for home and consumer use, where they mesh them in lower quality, and then you can have them also on your iPads or whatever you have at hand, right? So that's one of those systems. So the specs are quite impressive, right? So that's a purpose-built system. It has 32 cameras, 16 pairs of really high-end cameras with high-end lenses. And I think the likes of Tobias and I would be really jealous just to own one of those lenses, because they're very nice prime lenses. Each of the camera pairs is connected to a dedicated PC, plus PCs who control the lighting in it. And then I talked to Oliver about what it means to process all that information and to post-process the data. It's hundreds of hours post-processing per minute of produced volumetric video. But in the end, you get a really nice, high-end experience, especially when it comes to film production and broadcast quality. And also, of course, as you can imagine, the data throughput is quite high because of the high fidelity of it, right? A similar approach you will find with, I think almost as convincing, is the mixed reality studio, capture studio by Microsoft. You see here in that photos, it follows a similar approach. So you have a number of well-calibrated and high fidelity cameras, and you have controlled lighting. And then you bring that into a space, and then you capture your video content. And as you can see here, for instance, the same scenario, you render it in the end for different output devices. Could be your mobile phone, it could be immersive virtual reality experience or whatever it is. Or in that case, for instance, for the HoloLens experience. And this is, for instance, what also our nurses here use at the Otago Polytech for the training of the nurses. So they use exactly that system. One of the big advantages they always tell me is they can't produce their own content, right? So they rely on the content. In that case, they have a couple of scenes, a handful of scenes, which are produced exclusively for Pearson. That's one of the publishers, and they provide you with that system. But if you now, as a nurse, want to present a different case to the trainees, then you would have to go back to Microsoft, to the capture studio, and say, let's record that content, which makes it quite difficult. So again, specs in that case, it's 106 cameras, individual cameras, with also massive data capture throughput requirements, right? So we have also in the country, we have a company which follows a similar approach, probably a little bit more to the low end side of things, so not broadcast or film quality, but good enough to be introduced into computer games or as for casual users. The company is called ARIVE. Perhaps I have a video clip here as well, I think, yes. So it's a similar approach. In that case, they use only 30 cameras, and you can see that also in the meshed quality here. It's not as high-end as the Heinrich Hertz Institute system, but this is more on the side of things where even our nurses could go and say, okay, let's produce some content. It's not. It's probably at least doable. And this is, for instance, the company based in Wellington, so it would be almost around the corner. Or for some of you, it is actually around the corner. Same here, they have two different versions of their setup. So they identified that problem that you want to produce your content probably not only on that one location but elsewhere. So they have a stage setup which they have in-house. And then they have another one which they call a portable stage, and you can see that here. So you have to set up at a location, and then you can shoot your 3D or volumetric videos there. As you can see, the portable setup has to do with the calibration, and the calibration quality of it has HD quality, and the premium stage has a 4K resolution. So, but still the capture space is not super big, as you can see. I mean, the captured volume here is 1.5 by 2 meters on the portable side, and 2.5 by 2.2 meters on the premium side. So it's roughly what we capture actually with our system as well, but of course, higher quality here, right? Finally, there's one system which is quite high end, and that is it's called TrueView by Intel, and that's is not for video or film production, but it's for temporary replay of certain scenes in the NFL or also in football, in soccer. And so a number of Premier League teams now, or stadiums, subscribe to that concept now, like Liverpool did, and I think Manchester United did, and others. And so what you have here, you install static cameras in the stadium up to 38. Normally it is 38 5K cameras in the stadium, so they're well calibrated to each other. And then you do a voxelization of whatever you see on the field, and then there's a relatively short post-processing time, and then you can have a replay from different angles, mainly also for broadcasting or more interactive user experiences. So that's into TrueView. So of course, these are all quite high-end systems. So our system is a little bit more humble. So we use only 3 cameras, as I presented before. So, and I will show you roughly how it works with our setup, and in what kind of scenarios we tried that. And so, oops, that's the wrong one. Why isn't that starting here? I hope it's the right one. Yes, it is. So we recorded some musicians and different scenes, and with our camera setup, we mounted the cameras to the left, and then they're calibrated. Certainly calibration algorithms using our magic green. And then we record the voxel, and then the playback on either a virtual reality headset or So the question is that effective? Is that a very coarse voxelization compared to the other high-end systems? And we did a study on it in 3 different conditions or 3 different scenarios: music playback, language learning, and future. And
sorry, Holger, we can't really hear you with the music playing.
Oh, okay. Then
Rahm, cream, and geschnitzeltes cut-up pieces of meat, so the chicken in this case.
I see. Sounds delicious.
All right, we'll get that there. And yeah, have you heard of Thüringer Klößen? That's also what comes with it.
No, I haven't.
These are very interesting potato dumplings, a specialty of the region.
Okay.
Yeah.
Be sure your left hip is tucked in. Nice stretch for the IT band. Press up to extend your leg and grab hold from underneath your right foot. half lotus balancing. Extend your right.
Okay, so what you saw here, especially the AR version, was a little bit, layperson view filmed through the North Star head-mount display. So we didn't really have, better means of filming it, but it was like, really shot content. So as you can imagine, I mean, it worked it worked for the users, but the yoga and the music worked better than the language learning, and perhaps that can also be explained. Some content is better suited for the 3D video recordings or voxel video recordings than other content which can be shown in 2D and is as effective as volumetric videos. We also use the same technology in a project which we do together with the University of Waikato and the University of Canterbury. Rob is in part of that project. So where we do we record storytelling for Maori populations. So they want to record their stories, and then they want to give them to the next generation of people to be experienced instead of just as a 2D version. And I'm just playing one short video clip here where we see that one of the people involved in the project, so one of the leaders, Hemi Fanga, is explaining the Maori night sky as a voxel video. Oops, come to back. How do I go back? Here we are.
So the story relating to how the stars were placed in the sky relates to a quarter that goes back to Tamarereti, and he was the owner of the first canoe, and that canoe is still in the sky. It's over here in Scorpio's tail. So it's a small waka called Te Waka o Tamarereti, and he was the owner of that canoe, and he ascended to the sky with his brother Tane.
So what we can see here is, he is explaining the night sky. So in that particular case, Hemi is wearing the head-mount display while he is explaining it. So he is seeing the night sky. And so while it is played back, so you can take any position you want, as Noel did in that particular case, wearing the head-mount display, and can stand next to Hemi or can follow what he is pointing at, and so on and so forth, right? So it has that three-dimensionality of the experience. Okay. So our more recent versions of it is that we slowly switched from Kinect cameras more to the more affordable and available Intel RealSense cameras, as you can see on that photo here. So in that particular case, we are using 3 cameras to just capture the front side of objects, or in that case of people, and you see the checkerboard in it, which is just for the calibration of it, of the 3 cameras, the external calibration. So I'm playing a short video on that you see what kind of quality we can achieve, because with our standard Kinect setup, the best resolution we can actually get is between 6 and 8 millimeters per voxel size. And normally we settle on 8 millimeters for a number of reasons, but also because it's looking better than 6 millimeters. But 6 millimeters would be the limit anyways. So if we get closer with the cameras, in that case with the RealSense cameras, and they have a higher resolution, we can also get higher resolution recordings. And Noel, I don't know what that was. It was 2 mil, I think. There's 1 mil. That's 1 millimeter recording, because it's only the head and not a full room, right? So I'll play that one for you.
How are you? Kei te pēwhea koe. How are you? Kei te pēwhea koe.
So as you can see here, so the resolution is much higher, but still it requires actually quite a little bit of work, or a lot of work actually, into how do we calibrate that, how do we adjust the colors, how do we adjust the light, and so on and so forth. So there's quite a bit of research to be done, but I hope you already see the direction in which the whole voxelization of scenes is going, right? Okay. So this is the current setup we are using, and it's actually a portable setup. And that's so before we had the Kinect cameras, positioned in space, normally in our lab, and this is now a setup where we have the Intel RealSense cameras on tripods, and so you can take it to different locations, and that is at Stu's and Rosa's place at home. And so they added green screens to it, because it is actually because of the small baseline of the stereo baseline of the internal resense cameras, it's really hard to really reliably to separate the background out of the scene. So if you can use the green screens, and here they could, and you see still the checkerboard. So I'm showing a very short sequence of that recording with Stu in the scene. So this is what we roughly get. Still, you see some artifacts in it to be resolved, and I don't know what is the resolution. You have the same shirt actually on today, yeah. That's 4 mils. Okay, so it's a 4 mil resolution with that kind of setup. So the big advantage is that it is a portable. You can take it everywhere, right? And so I have some nice photos which actually Rosa and Stu sent to me today, because that was this morning at Dunedin's St. Clair Beach, where they put the system out there at sunrise. And you see it's a portable system, right? So, and actually Noel, Rosa and Stu went to the Marai and Bluff, to our partners, our Mari partners, and did story recordings down there with that portable setup. And Stu assured me yesterday that the setting up of the system, requires, depending on the circumstances, between half an hour and an hour. But then you are ready to go, and you can really record the scene. And that's quite a considerable difference to the high-end systems, which you normally would have to really set up into a room and calibrate them before, and so on and so forth. Lots of engineering. So, and also you can see a little bit of the beautiful beach here of the Dunedin city beach actually. So because some systems like ours, you can actually work in real time. So it's, let's say, with the Heinrich Hertz Institute system, with the Volucap. So as I said, it needs hours and hours and hours, hundreds of hours to post-process until you come to the final product, which is the voxelized, or later voxelized and then meshed version of the content. But some systems like ours, we do real time, and that lends itself to do co-presence applications. So we can actually meet in a virtual space while capturing people and bringing them into the virtual space. So probably the most well-known system of that kind of co-presence is probably holoportation by Microsoft. So they have 2 adjacent rooms. They have users wearing HoloLenses, and then they capture one side and the other side, and then bring them together into one room, and then can experience that with the HoloLenses. And that's actually a very nice system. It's not the only one, but it's probably the most well-known one. And so here you see roughly the specs for that one as well. So they have a so-called holoportation rig, and that consists on each side of 8 camera pods, and each pod consists of 3 cameras. So you have 2, you have an infrared stereo camera, you have an RGB camera, and you have a structured light just to help with the reconstruction. And so what it requires is actually quite high-end PCs. In that particular case, that was in 2016, each of the PCs was equipped with dual, I think, Titan GPUs. And so, but that realizes actually that real time, not post-processing requiring, like with TrueView or Volucap, but real-time transmission over a fast network connection between the 2 rooms, right? So again, our approach is the low-tech approach, and you see here Matt and myself meeting in space, in virtual space, and each of us is captured on one side in one different room of our labs. We have 2 rooms equipped for that. And the very first test we did with that one was actually, or one of the very first tests was with 1 Kinect each side between here and Anthony Steed's lab at UCL in London. And I just show you, no, that's the wrong one. And I just show you how I met Sebastian Friston from in London. So just, so our view is quite a little bit better because we look front on, but you see side views here. And of course, there's that latency. I come to that in a sec. But it was still a quite a very interesting and nice experience. And also, I think for you, Noel, to meet those people from actually the opposite side of the planet in that virtual space using that technology. So I have to say the main main hurdles haven't been necessarily the transmission of the voxels. Of course we had to reduce the bandwidth, but it was more about establishing the connection between here and London from an IT sysadmin's perspective, right? So you have to have, because we are running our own protocol, it's not, you know, like HTTP or any other well-known supported protocol. We are running our own protocols, so you have to link those two sides. But in the end, thanks to the support from the UCL side and our side, so we got it running. I show you another example here, which is the same principle, but with 3 connects on each side. That is Stu and Noel in our lab, meeting in virtual space. And I just play that one, hopefully. Yes, here they are. So it's an outside view. You see Noel down in that inset, and then they do some investigation. So and I stressed it again, and it's low res, and you see a lot of noise around it. Again, another research topic is to get rid of, you know, the noise while maintaining the truthfulness of the data, that we still see the people in it. And you see the coarseness of the voxels. That's an 8 mil, I think. I'm pretty sure, but yeah, it's 8 mil. Yeah, it's with the Kinects. And so what they even do here, they hug each other, which they normally don't do in reality, I think. Oh, do you? No, probably not. No. Yes, but it's a true 3D experience. So this is actually, it shows the potential of that kind of teleco-presence experience. Okay, so what we do at the moment with it is we try to develop that kind of idea, and so we have our own, you know, internal LAN, local area network connection here between our labs, and so we have the installations on both sides, and we use either our pre-installed Kinect systems, or we use the portable systems to make those telepresence experiences reality. We have still that existing connection to the University College of London. We have a second one now to Rob's HIT lab with, you know, Chris Tong with his PhD student. This is what we are now exploring more for the technical feasibility of the RTA ARIVE project, where the second focus is on telepresence for Mari, in addition to the storytelling. And then we want to install a system at the Mari down in Bluff, so that we can have a connection between the Mari here and perhaps the University of Waikato. And then we still have our old connections to the University of Oslo, where we already had the other system, or we already have the other system installed, so that we can really try out how teleco-presence works over a distance and not only in the lab, right? So, but there are some, I still have some, time for it. There are some probably considerations to be made when installing telepresence systems. So one is, so what is actually the ideal voxel resolution, right? So what kind of resolution do we want to achieve, perhaps? So we showed, actually Noel showed, that actually quite coarse voxels already lead to co-presence, for instance, experiences. But if you want to have other experiences, you might want to increase the voxel size, and of course we want to. So when we take the, you know, our natural, you know, capabilities of our eye, which is about one arc minute of resolution, and we would say, okay, we want to have, you know, objects at about a meter's distance to be, you know, as realistic as possible, and probably we need 1/4 of a millimeter voxel resolution, right? So that means, because it's all going in cubic, so it's actually it is a very ambitious goal, but it's achievable, right? We are at the moment at about, with the head and shoulders views at one millimeter. So it's probably doable within the next couple of years, given that the sensors will develop, independently of us, and so on and so forth. And we are also doing more to our, to our science and technology. But even if you just take, then let's say the current resolution of the head-mount displays, which is actually limited, then probably we play in an area between 0.5 millimeter to 2 millimeters, which gives us, you know, a realistic experience, assuming that we solve all the other issues like, you know, correct lighting and color correction and all that, right? So, but probably we are heading into the right direction when we say we are in that millimeter space with the resolution we are having at the moment as the best resolution, right? The second, a big issue is, of course, latency. for real telepresence applications, right? So one thing you can't beat, at least not with our current physics, is the speed of light. So, and when you, let's say you want to transmit something, whatever it is, over a distance of 1,000 kilometers, you will have a natural 6.7 milliseconds latency in it. So you can hardly do anything about it, right? That means, but it means over a real network, the practical latency is probably twice as long, right? So probably you have to count with 13 milliseconds for every 1,000 kilometers, which means that, you know, over a real distance, let's say of 10,000 kilometers, you already have 135 milliseconds. So 2 examples, Dunedin from here, New Zealand to Sydney would be 27 milliseconds, which is probably quite okay. From here to London is 240 milliseconds one way. So there are 2 things. So normally for normal interactivity in, you know, interactive systems, we aim for less than 100 milliseconds delay or latency in the system to have that, you know, to get that impression of a continuous interaction, right? Noel found out with his research that for those kinds of telepresence applications, you can actually tolerate up to even more than 500 milliseconds under certain circumstances, and if you're only after, you know, simple, you know, co-presence with the other person. But even if you take those 500 plus milliseconds into account as the longest tolerable latency, then it means our systems have to be very, very, very fast, because there's nothing left for our system, for our own system latency in terms of, you know, processing and calculating and sending over the network, right? So it's actually a tight game we are in for here. And when you even think, and you think about it when people talk about, you know, yeah, we do a jam session between here New York and Tokyo and Paris. Probably that's actually a very difficult thing to do given those latencies, because the musicians really have to be trained in predicting what the other person will do, and, you know, and how do you keep that beat, right? Okay. In terms of throughput, so admittedly at the moment our storage and transmission protocol is quite naive. So we take the voxels and we put them into an octree structure, and that octree structure is actually sent over the network. So it's not the raw data, but it's also there. We did not invest too much intelligence into the more intelligent, you know, storage and transmission of voxels. But let's say we take that as a starting point. Then we are at the moment with that talking head figure here, we are at about 1 mil resolution, so which means roughly about 250 megabits per second, say in a realistic scenario. If we want to go with that same protocol, let's say to 1/4 of a millimeter, we would already need 3 gigabit per second as a transmission. So that says we have to do something about it here, right? So we can't probably stick to that approach if the networking technology is not developing at the same rate. So it's even worse if we want to have a room, and in a room I mean really just what we normally capture, and that is what we normally now would capture between the 6 and 8 mil resolutions. That would mean if we want to go, let's say, to the 1/4 of a millimeter resolution, then we are more at that probably 90, 100 gigabit per second requirement. So at the moment not doable, but as I said, on the other hand, it's not that far out that we say we can never achieve that, right? So I think again we are here on the right track. Okay, summary. Yeah, I'm within time. So we do not always need high res. So it already works with the rather coarse voxel resolutions. And in some cases, we would even say, and we have some examples, and I have some in the miscellaneous slides here, that for some studies, it is even desirable to have a more abstract visualization than you know, a fine-grained, highly realistic presentation. But for other scenarios, we want exactly that, where we want to have the highest possible resolution. We will work on high res anyways, and we hope a little bit for Moore's law to kick in here. So the machine, so memory will be, you know, we get more faster memory all the time. And but still, for us, voxels are actually the logical consequential next step after pixels. So why wouldn't we do everything with voxels? So I have an analogy here. So back in the day, we had, vector displays, right? Vector displays like oscilloscopes, especially arcade machines, because they wanted to show, fine lines on their CRT, on their cathode ray tubes. They used vector displays. So they said, okay, a line goes from here to there, and then exactly that ray was drawn on the surface, right? So, but that when, the faster the computers developed, that was replaced by pixels in the end, right? We had such a dense pixel representation that we use pixels now for everything, right? We don't use those vectors any longer for the pure display, right? And the same is probably true now, and I postulate that now, that at the moment we are using all the, the 3D, the triangles, the meshing, but it's because we can't have that same effect with the volumetric pixels. They are not fine enough to show all those, those graphics. So if we would have, let's say, graphics machines and cards, and which would natively, genuinely support volumetric pixels for interactive applications, then probably we can actually replace a lot of triangulation work with voxels. We are not there yet, apparently, but that is probably where we might go. And this brings me to the end of this lecture, and I'm happy to take questions.
I had one question, Holger.
Yeah.
When you're thinking about meshes, I know some of the approaches for compression use repurpose like video codecs, maybe not 265 or HEVC. Is there any way to do that with voxels, or do you have to come up with your own?
No, actually, we discussed exactly that for many times. Actually, the Microsoft approach is using something like that. So they are using actually video codecs to, purpose or tailored, changed video codecs for their own storage and transmission. We discussed it here as well. So there are a couple, you can do that actually. You can use, for instance, let's say motion JPEG in motion JPEG, for instance, but we don't get the same intelligence about, let's say, on a 2D screen. You have certain features which lend themselves to nice compression in 2D. And now you're in the naive approach, now you can sequence them, right? Just, but it's not that we find the same features necessarily as manifolds in the 3D space. But as a starting point, and this is what Microsoft is doing, they just use that, and then we use those codecs. But you're absolutely right. But it would be one research area to really work on.
Just to extend that a little, MK 2000 that has a 3D right in its spec, but there's no implementation. There's no reference for external implementation.
So you found your PhD topic. Yeah, but you are right. So we should use that as much as we can. Yeah, at the moment, our proprietary, more naive approach is more Stu's brainchild. Yeah, which is good. It works. Yep. Yeah.
Hey, Holger, it's Mark here. I had a question for you. So it seems like with the voxels, of course, you have very nice, well, almost real-time performance, but the resolution is a little, of course, voxelated, so it's a little bit coarse. Have you also looking at doing some deep learning techniques where you could take the voxels as input and produce a high resolution output? So, if I've already captured your face or captured your clothing previously, then if I can see something that looks like your face, then I should be able to map face pixels onto the voxel and produce a higher visual quality output.
Yep. Yeah, thanks, Mark. Great question. And so we discussed that all the time, a little bit. I mean, not that particular idea. It's a great idea to do it. So there's a little bit of a philosophical question going on here. So one of the arguments, I didn't bring it today, but one of the arguments why we use, let's say, voxels instead of, let's say, computer-generated avatars, which are, let's say, a rigged texture to the avatar as another extreme, and I come back to your question in a sec, is that we are afraid of the uncanny valley. I mean, we are not there, not by a long shot, but the closer you get to the real representation, you want to keep the truth or to maintain the true data as long as possible and not trying to map that into something else, right? So when you see those very coarse voxel videos, probably, and now I come back to you, it would make sense to use something like, the technique you just described, just to make it look better. But from a purist point of view, I would say we shouldn't do it. We should try to massively improve on the capturing and the voxelization and the display of it, instead of trying to find workarounds or cover up deficiencies in our data or rendering approach. And I know that we can't show that yet with our approach, but otherwise, yeah, it's logical and to do it a little bit more in that way, and it might be a good topic for someone. Yeah.
I mean, I think you could also look at a mixture. So, for example, you could say, well, we want to be able to render people's faces, and so we'll use the real voxel data for that. But we're not so concerned about the furniture, and we're happy to take out the furniture and swap it for CAD models using some deep learning techniques to recognize the furniture, for example. Because if you're sending that data, that's another problem, because you have to send massive amounts of data to in a teleconferencing situation. But there are probably some parts of the data, like face and hands, maybe, that are more important to have live, and other parts that could be, have been pre-captured because they're not going to be changing, for example.
Yeah, no, I totally agree. And actually, also with our own projects, for instance, with the RTR project with our Mari partners, we also start to mix scenes, right? We have, let's say, we capture, the real Mirai as a triangle. So we triangulate, we produce a point cloud, and we mesh it, and we decimate it, and then we have the environment is actually a meshed model in the end, and the characters telling the stories inside of the Mirai are voxelized characters. But even if we could even go one step further, we could say, okay, as you just proposed, we know the face would be, highest possible resolution and realism for the face, and even the clothing could be, something, approximated or whatever. Yeah, you're right. Yeah.
I have a question too.
Is it Rob?
Yeah. Again, every time I hear you talk about voxels, it's very clear how much passion you have for it. It's really great to see the research driving. So as I understand it, each voxel has one color, right? So you're not texturing a cube of any kind, right? It's just one color?
Yep.
Okay. Have you since a lot of what's captured is stationary, have you thought about just transmitting deltas? So for example, a table is probably not going to change. So you could send all the voxels for a table and it won't swim anymore. It will, you've transmitted it, you just say, well, none of that has changed, so I'm not going to transmit it anymore. And so I think there's lots of intelligent things you could do. The question then is, if some things are swimming and other things are not swimming, you're back to the same problem, where you have some things that look different than the other ones, and maybe people have problems understanding that those occupy the same space. But probably to get around some of the limitations of volume, the volume of data you're going to need to transmit, you're going to have to, or I think it would be smart to resort to techniques that have been tried in terms of non-voxel based shared environments, which is only send the stuff that you need to send. And so, but I wonder, again, it's a good PhD topic. So I'm just wondering what you've done in that area, what you think about that.
Yeah, thanks, Rob. We haven't done anything in that area. Of course, we are discussing it because it's it's one of the major bottlenecks. So I agree. So we don't have to transmit everything as we do it with our more simple or naive approach at the moment. I could even take your idea now and extend it and say, okay, we sent the table as voxel data because it won't change or barely change, and we send the noise functions with it, so that we can even fake it on the other side if we want it. That would link to somehow to Mark's idea that we say, okay, some things are more important than others, and you would get still a kind of a coherent experience on the other side, because you would not really know how much noise, temporal and spatial noise, is actually there in the real environment. So actually, we could do that. We could do that. Yes, and you're right. Perhaps you just defined another topic here, right? Yeah. but we need to do something about it instead of just waiting for the machinery and the bandwidth to be there. So we need some more intelligence here. And one aspect we are doing at the moment is, especially for the body models, we also label each of the voxels where it belongs and where it comes from. So we can actually have a more, we call it semantic voxels. So we do have a more of an idea what needs to be transmitted all the time and what can actually be more stationary or what can be compressed more and so on and so forth. So we're quite aware of that. And there's also CAD libraries now, like 3DNet and stuff like that, where you can actually also generate geometries and then transmit them or just load them up at different sites at the same time and then apply the noise functions or whatever. Yeah, no, but good point, good point.
My last question was around rendering. So you have all these voxels, which is great. Are you using a voxel renderer? Are you then converting it somehow? And are there any limitations or things you could take advantage of? Are specific GPUs or GPU languages better suited to rendering voxels? What are you doing about?
So actually we are so we have Matt here implemented our voxel renderer, because we normally with the we could not render with, let's say, the normal game engines we normally use like Unity or Unreal. You only can render a couple of thousand voxels natively. So Matt implemented a two different shader-based voxel renderers, so one for Unity and one for Unreal, and those are the ones we are using. There's still room for optimization even here. So we had in the Unity one, we measured it, and I think we came to about 700,000 voxels in real time with 7 million with what latency? What was it about, or with what frame rate? I mean yeah, 94 we are. You have that 7 million. Yeah. So, but that requires the shader. It requires a special shader implementation. So I mean, there's no native support for it, but we have it for the two main platforms now. Yeah. Mm-hmm. Okay. If there are no more questions, and we are running out of time anyways, thank you very much. Thanks for listening, and I hope you will consider voxels in the future, because they are the future. Okay, thank you very much. Thanks for listening, and we see each other on Thursday, and we will have our colleagues from the University of Queensland talking about sensors and how they are integrated into the XR environment. Okay, thank you very much.
Thanks a lot.